So we're going to find the antiderivative of e to the z times sine of z dz. And this one involves a neat little trick that you can use, this particularly when you have a product of two functions that when you take either the derivative or the antiderivative, they never get easier, nor do they really get harder. They, for the most part, stay the same. The derivative and antiderivative of e to the z or e to the z. Derivative and antiderivative of sine are just trig functions, most notably cosine. So what we're going to do is we're going to do a u substitution. So here we're going to, we get to pick u and we get to pick dv, and it really doesn't matter which ones we pick in here. So for u, I might choose e to the z, and for dv, I might choose sine of z dz. Now du equals e to the z dz, and v equals negative cosine of z dz. And we'll go ahead and put this together with our integration by parts. So the product of u and v is a negative e to the z cosine of z minus the integral of v du. So negative cosine of z, that shouldn't have a dz there, excuse me, negative cosine of z e to the z dz. I'm going to clean this up in one step here. So negative e to the z cosine of z minus a negative, so I'm going to just change that to a plus. And to write it in the same order we had it before, e to the z and then our trig function cosine of z dz. And what you should notice is our integral involves a product of an exponential and a trig function again. So we're going to do integration by parts again. Now one of the things at this point, the order that we pick u and dv does matter. So I'm going to show you the order we should pick them in, and I encourage you to try the other way to see what happens. It's actually pretty interesting. You still get a true statement, it just doesn't tell us anything. But because I picked e to the z to be u in the first place, I want e to the z to be u again. And that leaves cosine of z dz for my du. Well then, just like last time, that makes a u of e to the z dz. And this time we get a v of sine of z. So let's put that back together and see what happens. So we have negative e to the z cosine of z from last time, plus now our uv is e to the z sine of z minus the integral of v du, which will be e to the z from here times sine of z dz. Now if we look at what's going to happen here, we got back to where we started. So, first thought might be, well, geez, what am I going to do? Do this again and keep going through the same process? Well, remember, this line here is exactly equal to this line here. This is what we were trying to find. So I'm going to bring this down, e to the z, and here's the little trick that I don't think is really obvious if you hadn't seen it before. I'm going to add this quantity to both sides. As long as I do it to both sides, our equation still holds true. So that cancels out over here, and what happens is I end up with 2 times the integral of e to the z sine of z dz equals negative e to the z cosine of, z plus e to the z sine of z. Remember, this is what we were trying to solve for, so my last step is I'm going to divide both sides by 2, and now I've got my antiderivative. So it's a little tricky to realize that that's the step we need to take before you've ever seen it, but now you know if you have a product of an exponential and a trig function, this is something that we can use to help us find the antiderivative.